Okay, back at you. So, we compared the difference between two group means. This is probably the easiest kernel, and this would be your point 4 within hypothesis testing, was what if we wanted to compare group proportions? Okay, so what if we took, so something like, we wanted to compare liberals and conservatives in how, what percent of liberals considered the COVID outbreak, I'm trying to think of something like current. What percent of liberals consider the COVID outbreak, a public health crisis, and then what percent of conservatives feel the same? So there's been a lot written about, how, different political beliefs and this whole, this whole outbreak and seeing like how desperate is the situation, I guess. So, I mean, but think about, what you could say, the proportion, what if you want to compare men and women and the proportion of men who vote Republican and women who vote Republican, or men who have college degrees and women who have college degrees. It's the same thing. It's literally, it's the same. You're still comparing two groups, but before you were comparing two group means. Now we're going to compare two groups' proportions. And the key difference is that with the group means, we use the t distribution. With the group proportions, we go back to our old friend z. Okay. So, hypothesis testing. So, again, we got to make the same assumptions. Oh, I'm sorry. One thing I will say, so everything just to differentiate things that we're doing, when we compared the sample mean to the population mean, only interval ratio level variables. When we compared two group means, only interval ratio variables. Why? Because we only calculate means for interval ratio variables. Here's your stuff with nominal and ordinal variables. So we can describe like a nominal variable by proportion. I mean, it could be something as simple as you compare men and women in terms of the proportion who like chocolate ice cream. This is the only place where you can use the nominal or ordinal variables, because proportions we can do for nominal or ordinal. We could do for interval ratio too, but we can only compare the means for interval ratio variables. So this is the only bit that will deal with nominal or ordinal. It's the same logic. Good news. Yay. Okay. So same thing. You want to make the same assumptions. Independent samples. They're random, and they're not generated from the same sample. Right? They're independent. Stating the research and null hypothesis, this looks exactly the same as the comparison of the group means, except for now you're comparing group proportions. I don't know why I felt like putting let's fix that. Sorry about that. There's another typo. So this would be not equal to, right? Let's see, add in a symbol. Not equal to. Right? So your null hypothesis is going to be that the proportion 1 is equal to the proportion 2. Your research hypothesis will be that proportion 1 is not equal to proportion 2. For a two-tailed test. You could do a one-tailed test with this too, where you have greater than or equal to, like if you had proportion 1 less than proportion 2, or proportion 2 greater than proportion 2. But just for now, just obviously it follows the same format as this above, right? I mean, it's just you're comparing like your null hypothesis is always going to be that the two groups are equal in terms of their means, and then the research hypothesis is that they're either not equal or less than or greater than. Same thing with the proportions, and then pi is your proportion, which I think it was T-Boat. I think you had trouble with pi, because pi is is a numerical thing, and using it as a symbol is a little funky, but I don't know. We'll let that slide, I guess. Okay. So same thing. Make the assumptions, state that, write them down, then select the sampling distribution. For the difference between proportions, we use the z statistic. In contrast to the difference between two means, we'll use the t, as before. The formula for computing the z statistic for proportion is relatively easy. It's just proportion 1 minus proportion 2 over the standard error of the proportions. Okay? So just like before, your kind of tricky equation was the standard error estimation. But this one is actually a little kinder, I think. But again, I mean, we're literally just talking about, I mean, here's the proportion of group 1, proportion of group 2, sample size of group 1, proportion of 2, sample. I mean, they're not, it looks more complex than it is. So you do the same thing, you calculate it, compute the test statistic, and make the decision. So what I want to do is work this one out. So I went to Pew Research Center, is an independent think tank. It's a reputable data source that gives information about demographics in the United States. As you can hear, I'm already getting some more emails. But so what I went to the website and I found that the proportion of first-generation Hispanic Americans with a bachelor's degree or higher was 0.11. So basically, 11% of first-generation Hispanic Americans had a bachelor's degree. Whereas in the second generation, that proportion goes up to 21%, or 0.21 would be the proportion, 21%. And here's your 2 sample size. The question is there a significant difference between first and generation Hispanic Americans in terms of their education? So are we seeing more education across generations for Hispanics, or are they saying the same? What do we see? So let's work this one out. There's not a good example of this in the book, so there is, but there are none. I tried to focus on the questions that are odd numbers, so you can look them up in the book. There are no odd number questions that deal with this, at least that I could find. So let's do this. Okay, so here's our z calculation. Okay. So that's the equation is z is equal to p1 minus p2 over the standard error of the difference. Standard error of the difference, right? And then in order to get that, we had to use this as a p1 minus p2 is equal to square root of p1 times 1 minus p1 over n1 plus p2, sorry, times 1 minus p2 over n2. Okay. Nothing tricky there. I just wrote out this equation so you can see it. Okay. So the first thing we got to do is estimate this. And this is really straightforward. Okay. So P1 is just going to be 0.11 times what's 1 minus 0.11 over our sample size for first generation was 899. Okay. Plus the proportion for the second generation Hispanics, 0.21 times 1 minus 0.21. 21. Can you read that? That's 0.21. Divided by 351 was the sample size for second generation. Square root the whole business. Okay. So when you multiply, let's just do 0.11 times 0.89, 899, plus 0.21 times 0.79 over 351. All I did was subtract 1 minus 0.21 and then 1 minus 0.11 there. Everything else is the same. Okay. 0.11 times 0.89, we're going to get 0.0979 divided by 899. So all I did was I multiplied these two. Plus 0.21 times 0.79, we're going to get 0.1659 divided by 351. Again, that's just 0.21 times 0.79. That's all I did. Okay? See what I mean? The math, there's nothing, the numbers are not hard. It's just, you got to stay organized with this. And I really think like writing every step of the way down, it'll help you avoid little, little tiny mistakes. Okay, so what you're going to get here, when you take 0.0979 divided by 0.899 and then 0.1659 divided by 3.51, calculate that out, you get 0.000108. And I will warn you, with these, you're going to get really small numbers. Do not truncate your rounding. Don't round that to 0.0 or, just make sure you're including enough decimal points. And then 0.16 divided by 351, you get 0.000472. Okay, again, like don't round too early. And then when you add these two together, you're going to get 0.000586. And then you take the square root of that and you get 0.02409. Okay? And you're like, it's almost like once you get to the end of this problem, like, what am I even doing? Remember, you estimate the standard error of the differences in proportions. Why? Because we need it here. These we already know. We just need that. So now we're set to go. And we just put in z is equal to, our proportion 1 was 0.11 minus 0.21. This is the proportion of first generation Hispanics with a college degree, second generation Hispanics with a college degree. And then we already calculated this. We got our estimate for the standard error of the differences is 0.02409. This is going to be negative 0.1 divided by 0.02409. All I did was subtract these two. And I'm going to get a value when I divide negative 0.01 divided by 0.02409. I'm going to get negative 4.151. And what is that? That's our estimate for z. So that's our test statistic. Okay, so now we're going back to, the z table, old reliable z table, as I like to call it sometimes. It's a good friend. So here's our test statistic. In the question I asked you for, did I ask you? No, see, I didn't even ask you, but typically I'll specify what confidence, what alpha is, what confidence level. In this case, I don't have one, so let's just take a look at how that works out. So we've got a z of negative 4.151. And again, remember that the z table is symmetrical, so we don't, if it's negative, we can treat it like a positive. It's symmetrical on either side, so don't get hung up on that. So where we be looking, remember, we want to look at the area beyond z, because we want to see how, if our value, what proportion of expected samples would be outside the value that we get. The other way to do it is just think back to, remember, a 95% confidence level, z is equal to 1.96, 99, you could just commit these to memory, 2.58. And you do the exact same thing. If your z statistic that you obtain is higher than the z value, then you reject the null. Remember before with the last example I did, the t, you had a t test statistic that was less than the critical value. So you went with the null. This case, we have a z statistic that's higher than the critical value, so we reject the null. The other way to think about that is when you look up the z equals 4, you can see that the area beyond z is less than 0.0001. So we're super confident that that difference is meaningful. Basically what it's saying is that if we plotted the proportion of college scores for first generation, and we could do this, I could ask you to create a confidence interval for first. What it's saying is that the second, this is 0.11, this is 0.21, right? That's what I said. What it's saying is that the confidence intervals do not cross over each other. So we can be sure that they're different. So your conclusion here would be we're 99% confident, because that would be the z equals 2.58. We're 99% confident that the difference between first and second generation Hispanics in terms of education is significant. And then you could even go back and say that second generation Hispanics have a higher proportion of college degrees within their population. That's the conclusion. So you would go back to the research hypothesis. That's what you're going with, and you know that the group differences are significant. Okay, I know that's a lot. I think that I'm going to upload your homework for you. I think in practicing it, it'll become more clear. Let me just go through the summary of all of this. So with hypothesis testing, we did 4 different things. We compared a sample mean to the population mean. if we know this population standard deviation, we go with Z. The second thing we did was the same thing, the sample mean versus a population mean, but we don't know, then we use T. If we don't know the population standard deviation, then we use T. The third thing we did was we compared two group means. We looked at sample 1 versus sample 2 as a way to say something about the population of 1 versus the population of 2. If we're comparing means, then we use a T. The second thing, the last thing we did, second thing today, the last bit of the chapter was comparing proportions, so sample proportions, which really represent population proportions. And in that case, we use Z. So maybe I'll just put this on here. I don't know if this helps. I like to think about things, this is the big picture, the so what. So the first two are really the same. You're comparing a population mean to a sample mean, or you're taking a sample mean and comparing it to the population mean. The decision comes down to whether you know the population standard deviation. If you do, Z. If you don't, T. What you're going to find is that this is typically the case. The third case was we're no longer comparing a sample to the population. We're taking samples of two groups, which represent the population of two groups, and comparing the two groups to each other, men versus women, first generation versus second generation, et cetera, et cetera. If we're comparing means, we use a T statistic. This is only for interval ratio variables. If we're looking at proportions, which could be nominal, ordinal, or interval ratio, proportions that we get from the sample which represent the population proportions, then we're back to Z. And I pulled this little website for you. It's right here. So how to decide between T and Z. Again, probably the most common question I get on this thing is, how do we decide which one to use? I like things like this, little decision matrices. So like, what type of data? Do you have means or proportions? That's the first question. What you're gonna see is, like, as we get through this, like every time I'm gonna focus on means and proportions. Why? Because means we use only for interval ratio variables, but sociologists are interested in nominal or ordinal variables typically more. Most of the variables of interest are nominal or ordinal, so we use a lot of proportions. So moving forward, it'll be like I'll do the procedure for means and I'll do it for proportions. Same thing here. So are you looking at means or proportions? And then here's sort of your decision test. So is the population standard deviation known? If it is, then we use the Z. If it's not, then we use the T. So hopefully this helps, but this bit also I think will be helpful. So just to know whether you use the Z or the T. So that's it for today. I'll put the homework assignment up. Do your best. If you have questions, let me know. The other thing I'll say is that I really just want to make sure that y'all are, engaging with the material. It's tough, but do your best. If you have questions, email me. We can talk on the phone. We can, we'll figure it out. But don't get too hung up on these scary looking equations. Like I worked them out. It's really just the numbers aren't hard. It's just kind of staying organized. So anyway, we're about 20 minutes here. So the two videos combined at 50 minutes. So enjoy viewing those. Anyway, have a good weekend, and I don't know if y'all saw, but the governor ordered a shelter in place starting at 6 o'clock this evening, which will last till the 13th. So, get stocked up and stay in your homes. So anyway, good luck with everything. Hope everybody's staying safe and healthy, and I will upload another video for you on Tuesday. Bye.